Good afternoon. I'd like to spend the next roughly 10 minutes or so just interrogating some of the things we believe about LLMs and how they're different from machine learning. I had ChatGPT do something. I had ChatGPT generate some sentences about the impact of generative AI or large language models, but I replaced large language models with a different, still applicable technique. I think if you take a second to look at these sentences, you might agree that they're true, but it's hard to imagine reading these in a popular press report. But it's not hard to imagine reading these sentences if we replace the green text with large language models. Why is that? What is different about these large language models? Well, people have proposed a number of factors that might be different about large language models. One of them is that the raw output of large language models may be unsuitable for our application. We might have hallucinations, we might have toxicity, we might have reputational damage if we just put this raw LLM output out into our application. Another one is, as we saw in that excellent demo by Kirsten and Valentina, we may need additional context to satisfy a user's request with LLMs. We have this pattern of retrieval augmented generation where the LLM can't know everything about our data, but if we add in data as context, the LLM can actually answer a user's question. And then the third one is that LLMs deal in natural language. So we're programming them by asking questions in natural language. We're not doing all of this sort of laborious feature engineering that we do with conventional ML to get a good result. So let's look at each of these in turn and see if they're really how LLMs are different from ML systems. We'll start with guardrails. So we've all seen cases where LLM systems need a guardrail in order to have appropriate outputs. Do these apply to other machine learning systems as well? I'd say that they do. Consider autonomous vehicles. You may have a computer vision model in an autonomous vehicle, and its raw output is not suitable to have a safe autonomous vehicle on its own. You need to have some rules that govern the behavior of the vehicle independent of the outputs of the model. Now you might say to me, Will, autonomous vehicles, that sounds hard and dangerous. I prefer to do more conventional machine learning applications that don't involve human lives. Okay, fine. Let's consider retail recommendations. Right? If you're running a recommendation engine for a retailer, you can't just use the output of that recommender model out of the box. You need to augment it with rules about your business, rules about what you have in stock, rules about what you can actually ship to that customer if it's going to be useful for solving your problem. Similarly, if you have a forecasting model that you're using for pricing, whether you're pricing products, whether you're pricing securities, whether you're pricing ad auctions, we need to put guardrails around that as well, especially if we have a market with multiple algorithmic participants in order to ensure that we're insulated from consequences of these models going off the rails. Now, even if we go to the very simplest machine learning model we can think of, like a linear model, we need guardrails. We can't just take the output of the model and put it into production right away. And here what I have is some synthetic real estate data based on the median price of a house in the United States, which is $124 per square foot. That should be a laugh line here in Manhattan. But let's make it a thought experiment and say, what if we want to extrapolate from outside of our training data and extend this regression line down to that 150 square foot mark? If we just put this simple model into production without a guardrail around it, we've just eliminated the self-storage industry. So even with the most basic model you can think of, you need guardrails once you go into production. Okay, well maybe guardrails isn't the difference. Maybe it's that we often need extra context for these LLM systems. And retrieval augmented generation has led to a lot of cool use cases, but this is also a pattern we see in machine learning systems elsewhere. Think about fraud detection, for example, in consumer payments. My bank is going to know where my last dozen in-person transactions are. And they can use this information to say, hey, if your next in-person transaction is spatially near your last dozen in-person transactions, that's more likely to be you than not you, for example. Similarly, if we think about media recommendations, how many people have gone to Spotify's on-repeat playlist and gotten feedback so that all those songs just stay at the top of your on-repeat playlist, right? Even in the context of something simple like this, you can use additional context. And in machine learning systems, we're supporting that additional context with a feature store. In LLM systems, we're supporting it with a vector database usually. But in principle, this idea that you might need something other than the point information you have in an inference request to answer the question is true for both ML and LLMs. Okay, well, feature engineering, this has got to be where we see the difference, right? If you're dealing in natural language, you don't need to do this thing that you have to do for machine learning models where you're going to transform and encode carefully your data to get a good result out of your modeling technique. And not only that, but you have to worry about different kinds of models. If you're doing something for a linear model, it's going to be different than what you're doing for a tree ensemble, probably. Well, in LLMs, we may think that we get away from this, but we may have to do it anyway. And think about how you interact with LLMs or how you've seen people interact with LLMs. There are all kinds of these magic incantations that go into prompts, right? Like telling the LLM what it is and how it should act, or telling the LLM how to give you an answer, or even just pleading with the LLM by saying that something bad will happen if it doesn't answer your question, right? Like these things all happen, and they give you different results depending on which model you're using. There are even a lot of cases where there are model-specific tokens that you can use, and if you know how a model was trained and how it's supposed to be used, you can get better results sometimes by using these model-specific tokens. So whereas we're not dealing with feature vectors where we would with a conventional ML model, we still need to do a lot of model-specific data preparation and a lot of experimentation to identify the right way to use LLMs for a given application and the right way to use a given LLM for a given application. So where does this difference actually come from? I'm going to ask how many people in here have not seen this picture before? Okay, a few of you. So this comes from a about 10-year-old paper. And basically the thesis of this paper is that machine learning techniques are relatively simple, but machine learning systems are relatively hard. And if we think about machine learning models, models are celebrities, right? Like you can name dozens of models, right? You may not care as much about all of the stuff that goes around those models and makes it possible to build machine learning systems. But the argument of this paper is that this stuff is all the hard part. And the argument I want to make in this talk is that all of the things that people say are different about LLMs are actually problems you only run into when you build a system. So think about how we built ML systems before LLMs. We sort of started off formalizing our problem. We got into what we think of as this sort of core data science inner loop of feature encoding, choosing and training a model, validating and simulating to make sure that we got good results with out of sample data, and then deploying in production. And a lot of the challenges of deploying in production are working around things we missed on that left part of the diagram, right? Working around things that can go wrong in the real world that don't go wrong in the lab. Now, the interesting thing about LLM systems is that we often start in the middle by choosing a model that someone else has already trained. So the emphasis is no longer on choosing a machine learning technique, and we're free to think about all of these concerns that only go into building systems. Another challenge that we see with LLMs is that we have to think a lot more about business metrics even than we do for ML applications, because actually doing model metrics can be pretty hard and pretty expensive. So I think the way to see this system, this situation, is that machine learning techniques are relatively easy, but machine learning systems are relatively hard. A lot of the challenges we see as potentially unique, a lot of the challenges that we as a community might believe are unique to LLMs are actually challenges of just building machine learning systems that we may have ignored for other machine learning applications because we were focused on choosing the right technique. With LLMs, we often start with a trained model and have that flexibility to tune and really think about application level constraints and system level constraints earlier. So they bring these systems issues to the forefront. But a lot of the systems issues we have to solve have analogies in the ML systems world. So the work you've done in the past to build ML systems, you can build on it as you're building LLM systems. Thanks.